Hello! Welcome back to Adventures in Linear Algebra, Null Spaces, and Consistency by Michael, Ibrahim, and another Michael. But this time it's just me. So, we're going to be covering consistency. So, uh, what does it mean to be a consistent system? Well, some basic properties of a consistent system are one, that for a system to be consistent, there must be at least one solution, although there can be many, up to infinity. There can be infinitely many, but there must be one solution. An inconsistent system is one that does not have any solution. A dead giveaway that a system is inconsistent is if you solve for reduced row echelon form and you get a false equality statement such as 0 equals -3, that means that there is no solution because that statement is not true, and therefore that system would be inconsistent. One trick we can use to tell if a system is consistent is if there are more variables than there are equations in the system, then it must be consistent because having more variables than equations means infinite solutions, which would mean there's at least one solution, which would mean that it's consistent. In the previous video, we talked about homogeneous systems. It is noteworthy that all homogeneous systems are consistent. Alright. We are also going to need to understand some ideas about column vectors and column spaces. Let's say we have the equation ax equals b. That system will be consistent if and only if b can be expressed as a linear combination where the coefficients of the linear combination are solutions to the system. So, we basically have each column multiplied by a coefficient, and that will be set equal to a b column. We'll demonstrate this on the next slide. It also says that the system ax equals b is consistent if and only if b is in the column space of A. And that will be an important property to note for our final conclusion for this example we're about to do. So here's our example. We are given the following augmented matrix. This linear system, we are told, in our example, is consistent, which is true because if we do reduced row echelon form, we see that the bottom row is all zeros, which means that this has infinite solutions, and therefore will be a consistent system. And then we are given the second system, which is nearly identical. All the values are the same except for the last row, which in our system expresses ax equals b, would be our b column. The last row is different, but, well, the last column, last row, or bottom row, is 0, so that part's the same. But the 3 and 1 and the -9 and -3, we can obviously see that for this blue matrix, it's just a scalar multiple. It's 3 times -3 and 1 times -3 to give us these values. And here's the reduced row echelon form. But we want to show that this blue matrix is consistent without necessarily solving it. But we will do some solving just to dive deeper into the ideas. So, what we want to do is find that linear combination of vector columns as described on the previous slide. And we've done that here for both matrices, blue and green. So we put it in the form as described, where we have our coefficients times each column equals the b column. And if we solve for these coefficients, we get that in both cases x3 can be a free variable, and x2 and x1 are sort of relative to x3. Like here, x1 is 1 plus 2 times x3. And we can pick any number for x3, plug it in here, and we'll get coefficients for x1, x2, and x3. If we plug in those coefficients and multiply this all together, no matter what we chose for x3, these three columns added together, multiplied by their coefficients, will give us 310, and the same is true over here. Okay, so how does this all come together? Basically, B is a subspace of the column space of matrix A. Since the value for B in the blue matrix is simply a scalar multiple of the B vector in the green matrix, both values of B are part of the same subspace of solutions. Therefore, consistency is shared between both matrices. Basically, that boils down to each B column is within the column space of its respective matrix, and the B columns are just scalar multiples of each other. So they can be considered as being part of the same subspace. And since the B columns are the only thing different between these two matrices, and we know that within a subspace scalar multiplication is closed, those properties allow us to come to that conclusion that both these values for B, both these columns, can be considered part of the same subspace. And since that is the case, we can say that since this matrix is consistent, this matrix must also be consistent. Thank you for watching.